Alright, welcome to the first real video in my Linux Insights series where I read through this publicly accessible free resource that goes in depth into Linux. So we're going to start by learning about the booting process in Linux. And we're just going to read everything out loud. So this is the kernel boot process. This chapter describes the Linux kernel boot process. Here you will see a series of posts which describes the full cycle of the kernel loading process. So we're going to go through each section at one. Not sure how I'll organize this playlist, but the first section is from bootloader to kernel, and it describes all stages from turning on the computer to running the first instruction of the kernel. So I'm not going to read the rest ones. We're going to start here. This will probably take the full length of this video. Okay, so this is the kernel booting process, part one, from the bootloader to the kernel. If you read my previous blog posts, you might have noticed that I have been involved with low-level programming for some time. I wrote some posts about assembly programming for x86_64 Linux, and at the same time started to dive into the Linux kernel source code. I have a great interest in understanding how low-level things work, how programs run on my computer, how they are located in memory, how the kernel manages processes and memory, how the network stack works at a low level, and many, many other things. So I decided to write yet another series of posts about the Linux kernel for the x86_64 architecture. Note that I'm not a professional kernel hacker and I don't write code for the kernel at work. It's just a hobby. I just like low-level stuff, and it is interesting for me to see how these things work. So if you notice anything confusing or have any questions/remarks, ping me on Twitter. So here's his Twitter account. Drop me an email or just create an issue within GitHub. I appreciate it. And I might be doing that during the course of this series, actually. So I'll sign into my GitHub and keep track of this. And if I find something, report an issue. All posts will be accessible at GitHub repo, and if you find something wrong with my English or the post content, feel free to send a pull request. Yeah, I think I'll be doing that. Note, this isn't official documentation, just learning and sharing knowledge. Okay, so we've got some knowledge requirements here. We need to understand C code. Unfortunately, I do not. I'm a network engineer, and that's really not relevant to the skill set of a network engineer. Then we need to understand assembly code. That's another thing where it's really not relevant to what I do. So we're just going to keep going. Hopefully that won't ruin things. Anyway, if you're just starting to learn such tools, I will try to explain some parts during this in the following posts. Alright, this is the end of the simple introduction. Let's start to dive into the Linux kernel and low-level stuff. I started writing these posts at the time of the 3.1x Linux kernel, and many things have changed since that time. If there are changes, I will update the posts accordingly. Okay, so the magical power button. What happens next? Although this is a series of posts about the Linux kernel, we won't start directly from the kernel code. As soon as you press the magical power button on your laptop or desktop computer, it starts working. The motherboard sends a signal to the power supply device. After receiving the signal, the power supply provides the proper amount of electricity to the computer. Once the motherboard receives the power good signal, it tries to start the CPU. The CPU resets all leftover data in its registers and sets predefined values for each of them. The 803, 86, and later CPUs define the following predefined data in CPU registers after the computer resets. So this might be a reason why rebooting the computer tends to fix a lot of issues, because it'll reset the CPU to predefined data. The processor starts working in real mode. Let's back up a little and try to understand memory segmentation in this mode. Real mode is supported on all x86 compatible processors, from the 8086 CPU all the way to the modern Intel 64-bit CPUs. The 8086 processor has a 20-bit address bus, which means that it could work with a 0-0x FFFF or 1 megabyte address space, but it only has 16-bit registers, which have a maximum address of 2 to the 16th power minus 1, or 0xFFFF 64 kilobytes. Memory segmentation is used to make use of the address space available. All memory is divided into small fixed size segments of 65536 bytes, 64 kilobytes. Since we cannot address memory above 64 kilobytes with 16-bit registers, an alternate method was devised. An address consists of two parts: a segment selector, which has a base address, and an offset from this base address. In real mode, the associated base address of a segment selector is segment selector times 16. Thus, to get a physical address in memory, we need to multiply the segment selector part by 16 and add the offset to it. So the physical address equals the segment selector times 16 plus the offset. For example, if CS:IP is 0x2000 colon 0x0010, then the corresponding physical address will be the segment selector, which is here in hexadecimal. I'm not sure what this operator is. Plus the offset, which is here. So it turns out to be that. But if we take the largest segment selector and offset, then the resulting address will be this. So this is hexadecimal. So we've got, if we're familiar with binary, an octet in binary is 8 digits. So these are binary octets. I think this just says that it's just an identifier, that it's... Oh, I'm not sure what this is, though, because this is converting it to hexadecimal. So I don't know what this is. Is that... It looks like it's Python because it's these three things. Let me just open up Python and run that, because Python has a built-in help menu. Yeah, so we can get a help on hex. And we can get a help on So let's try this operation. Okay, so that operation worked. So let's try a help on that operation. Okay, this is just getting help on the output of the operation, which is an integer. Let's go to the help interactive menu. And then let's do symbols. And there, so we can see the symbol here. So let's get help on that symbol. So this is a order precedence symbol. The following table summarizes the operator precedence in Python from highest precedence. Oh, I guess it's not. I guess it's a I guess this is just, yeah, this is just showing the, oh, okay. So here we go. Here we got it. So this is not help on this operator. It's a help menu that explains the operator precedence table, which is right here. But we can see we've got this symbol showing up in the table. And we can see what this does. It shifts. So let's put that knowledge in the action, and we're gonna do hello world, and then we're gonna shift world. Okay. Let's try and okay. So we've got unsupported operand type. So I guess you can't use it for a string. Let's try it with an integer. Ah, perfect. Okay. So now we've got that working. I wish I knew more about. Let me go back to the help. Okay, there's the operator. Let's type in shift. Now this is like low level stuff. So a lot of this in my opinion, without knowing exactly what the operator does, is something that applies to like the bits. So like, let me just do a Google. There we go. Perfect. So this is the right shift operator. It's a bitwise operator. So it only works on things that are a bitwise representation of an object. And then the second thing you pass it has to be an integer. It has to be the number of bits that you shift it. So yeah, so you can change. Okay, so let's understand it like this. So here's the if we do a help on bin, we can see we've got a built-in function for representing a integer as a binary number. So let's take a look at what the integer 10 looks like in binary. Okay, so we've got this symbol here to represent that this is a binary string. And so we've got 2, 4, or 0, 2, 4, and then the 8's place. The 8's place is turned on, so we've got a value of 8. The 4 place is turned off, so we still got a value of 8. The 2 place is turned on, so now we've got a value of 10. and the 0 place or 1, this can represent 1 or 0, is turned off. So yep, this is our value of 10. Let's take a look at the value of 4. Okay, so now we only need 3 digits because we've got a 4's place, and the 4's place is on. That's what that 1 represents, that we're turning on a value of 4 because this third digit here is in the 4's place. So we've got the 1's place, the 2's place, and the 4's place. By turning on the place, you're representing the value of the place. So this is the 4's place, which represents a value of 4. It's turned on, so we've got a value of 4. This is the 2's place, represents a value of 2. It is turned off, so we don't have that value of 2. This is the 1's place, represents a value of 1, turned off. So our total number that we're representing here is 4, which in binary is 1, 0, 0. All right, so now let's learn what that shift does. Let's shift the 4 to the right 1. Oh, and it looks like we can't do that because the operator requires different data types than the ones it was fed. So which data types does it require? Which data types am I passing it? Let's start there. So if we do type bin 4, I'm passing it a string, and it says right here what I'm passing it. I'm passing it a string, and I'm passing it an integer. So I noticed they've got something kind of funny here. They've got b equals a. So let's just try 4. So now we've got, and we're going to shift it to the right 1. Okay, so that worked. And why did that work? Let's take a look at the. Oh, okay, I get it now. I get it. So let me explain this. And I'm going to blank this out, and I'm going to explain what's happening here. So here's the binary representation of 4, which is 1, 0, 0. Okay, now here's the binary representation of 2, which is 1, 0. So if we were to get rid of this, so basically you can think of it as shifting everything to the right and then cutting this off. So let's think of a cliff. Let's say that this quotation mark is the edge of a cliff. So we're going to shift it over, and we're going to throw this off the cliff. So now it's missing. It's thrown off the cliff, and we've got a new binary number, which comes from this binary number. It's just the same number, but with the last digit thrown off that cliff. So now this represents a value of 2 because the 1's place is turned off and the 2's place is turned on. So if we were to do that, if we were to shift it the other way, now I'm going to do a 3, 2, 1, and let's see. Let's try to guess what it's going to be. 3, 2, 1. Okay, so hopefully the answer everyone came up with was 8, because we're going to do the opposite. Instead of pushing something off a cliff, we're going to rescue from the cliff, and we're going to add a 0 here. So now there's an extra place, and this is shifted over to be in the eights place and not the fours place anymore. So if we reverse the sign like this and shift it by 1, we get a value of 8. So that's what this operator does. It shifts over the binary values by throwing a value off a cliff, or adding in a value, or adding in a placeholder value. So like changing the place. So like if you had a ones place, a twos place, and a fours place, and then you shift it to the right, now you're throwing one of those off a cliff. So now you only have a ones place and a twos place because you moved everything over and you threw one off a cliff. If you shift it to the left, now you're adding a place. So now you have a ones place, a twos place, a fours place, and an eights place. So hopefully that's clear. I understand it now, so I'm going to move on. Okay, so now we can make sense of this more. The segment selector needs to be in hexadecimal. So to get the hexadecimal number, we take the binary number, we shift it. So we're adding places to it. So we're adding 4 more digits to it. So instead of it being in the 8th place, it's going to be in the 128th place because it's now a full octet. We're converting that to hexadecimal, which will be FF from what I understand. And then we're adding a hexadecimal number. I guess I don't understand why it's why this is the result. Let me try this. So 0x 200 4. So that's the decimal representation of the binary number. Let's take a look at what that looks like in binary. Okay, so, oh, that's interesting. Why is that the case? Oh, okay. So that's the case because this is not a binary number. It's let's take a look at what it is. It's an integer. I don't know what the x means. Oh, you know what? It's a mathematical operation. It's 0 times. Oh, wait, no, it's not. No, because that would be this operator. Yeah, I'm not sure what's going on there. I'm not sure what that x means. Oh, you know what? It's because this. Okay, I understand. I was thinking this was binary. It's hexadecimal. It would be 0b if it was binary. So the reason it goes, I get it now. I don't understand why they need this. Oh, I see. It's because if you do this operation here, you get a decimal number. So they're converting this number to hexadecimal. Yeah. Okay, and then they're adding the offset, or yeah, the offset here. And then, okay, that makes sense to me now. All right, so moving on. If we take the largest segment selector and offset, then the result will be this, okay, which is 65520 bytes past the first megabyte. Since only 1 megabyte is accessible in real mode, 0x10ffef becomes 0x00ffef. So this here goes from 1 to 0 with the A20 line disabled. He's got a link here for A20 line. Perfect, right to the wiki. So I like that. I like that it's tied into a wiki, like the Wikipedia article like that. But I'm just gonna move on. As I said, like this stuff isn't super relevant, I think, to me. So like, I think mostly this will just be an inspiration to someone watching for who it is relevant. To look at this, dive deeper into it, or someone for who wants to get into, because that's what this channel is about, helping others build a career. So if somebody is interested in this, click these links, read through that Wikipedia on your own, and really dive deep. But for this series, we're just going to focus on this documentation and get through this, which I'm sure will take a long time, especially if I keep going on tangents. Okay, now we know a little bit about real mode and its memory addressing. Let's get back to discussing register values after reset. The CS register consists of two parts: the visible segment selector and the hidden base address. In real address mode, the base address is normally formed by shifting the 16-bit segment selector value 4 bits to the left to produce a 20-bit base address. However, during a hardware reset, the segment selector in the CS register is loaded with 0xf. So 0x means it's a hexadecimal number. So there's 4 digits in this hexadecimal number. So that means if it were a binary number, it would have 8 digits, because the digits here represent place values of so the first place value is 16. The second one is a value of 64. The next one is a value of 92. And then the next value is a value of 128. Each place value can be represented 0 through 15. So say we want to represent the number 16, we would have 1 0, because the value, the place number, the value number is switched on. The 16th place is switched on. The first here, this represents 0 through 15. So if we wanted it to represent the number 15, we would have an F here, and that represents the decimal number 15. There are 16 different numbers you can represent using one digit in hexadecimal. Those 16 numbers are 0, 1, 2, 3, all the way up to 15. If you want to represent the number 16, you need 2 digits in the hexadecimal number that you're using to represent the decimal number 16. You need the first digit reading from left to right to be a 1, so that the 16th place is on. And then you need the second digit to be off. So if you're going to represent the number 17, you would have the 16th place on with a 1, and then you would have the first placeholder digit here, which represents values of 0 through 15, set to 1. So you would have 1, 1. That is how you represent the number 17. To represent the number 18, oh wait, hold on a second. Yeah, then you would have 1, 2. And we can verify our work here using Python. So we can do hex 17, that's 1, 1, and then hex 18, 1, 2. So if we were to flip this one to a 2, now we're representing two values of 16. Oh, wait. Hold on a second. We're representing, wait, I'm confused. Let me just see what it is. That's the beauty of Python. You can just see. And so there's also, in addition to hex, there should be something to convert it to decimal. Let's do a help on. So this is an integer. Oh, you know what? It's int. So let's convert to an int. The hex. Or 0x, which represents hex, 20. Okay, so that's. Oh, I see. That's 32. This is 16. That's what I thought. Yeah, this is 48. So we're so this is the 16th place. So we incremented by 16 every time we increment the decimal number, or not the decimal number, but the number here. So if we have an f, our maximum value is 240. So the next place here, if we were to turn this on, now we get a value of 256 because this is the 256th place. To represent a value of 255, we need two f's like that. Okay, so I knew I understood this. It just it's a little bit. It's like not super relevant to know that. Outside from like a test at school. So all right, moving on. Especially when you have like a tool like Python and you can just kind of learn it on the fly using like the help menu and kind of get, and the thing is, like, even if you know it super well, in my experience, if you can use tools like that to kind of check your knowledge, like it helps, especially if you're like me and like a little bit ADHD and like kind of have to refocus your attention and kind of remember where you lost it. So, which is 65520 bytes past the first megabyte. Since only 1 megabyte is accessible in real mode, 010 FFEF becomes 0x hexadecimal 00FFEF with the 820 line disabled. Okay, now we know a little bit about real mode and its memory addressing. Let's get back to discussing register values after reset. The CS register consists of two parts: the visible segment selector and the hidden base address. In real address mode, the base address is normally formed by shifting the 16-bit segment selector value 4 bits to the left to produce a 20-bit base address. However, during a hardware reset, the segment selector in the CS register is loaded with 0xF000, and the base address is loaded with 0xFFFF0000. The processor uses this special base address until CS, which was not explained. It's a register. A CS changes. So CS is a register in the CPU, and it's not explained very well. It's probably something to do with one of these hyperlinks. Okay, so the starting address is formed by adding the base address to the value in the EIP register. We get this hexadecimal number, which is 16 bytes below 4 gigabytes. This point is called the reset vector. It's the memory location at which the CPU expects to find the first instruction to execute after reset. It contains a jump instruction that usually points to the BIOS entry point. For example, if we look in the core boot source code, we see this. So this is going to be in C. Here we can see the jump instruction opcode, which is 0xe9, and its destination address there. We also see that the reset section is 16 bytes and is compiled to start from the address 0x, that address there. Now the BIOS starts. After initializing and checking the hardware, the BIOS needs to find a bootable device. The boot order is stored in the BIOS configuration, controlling which devices the BIOS attempts to boot from. When attempting to boot from a hard drive, the BIOS tries to find a boot sector on hard drives partitioned with an MBR partition layout. The boot sector is stored in the first 446 bytes of the first sector, where each sector is 512 bytes. The final 2 bytes of the first sector are there, which designates to the BIOS that this device is bootable. Once the BIOS finds the boot sector, it copies it into a fixed memory location, jumps to there, and starts with an S, executing it. So this is in assembly. Build and run with this. Okay, so I think I want to stop. I've been reading this. Oh, let's get to the bootloader section. So build and run with this. Which would be great if I could use a like a VM and mess around with this. This will instruct QEMU to use the boot binary that we just built on a disk image. Since the binary generated by the assembly code above fulfills the requirements of the boot sector, we will end it with the magic sequence. QEMU will treat the binary as the master boot record MBR of a disk image. Note that when providing a boot binary image to QEMU, setting the origin to that, using that is unneeded. Okay. In this example, we can see that the code will be executed in 16-bit real mode. After starting, it calls the 16 interrupt, which just prints the exclamation point character. The times directive will pad that number of bytes up to 510th byte with zeros and finishes with 2 magic bytes. Which would be the it gets a lot because there's 246, so I'm not sure what that would look like in decimal. I can use Python to figure it out. Let's do that actually. So int 0x a, that would be 170 in decimal, and then 55. That would be 85 in decimal. You can see a binary dump of this by using the objdump utility, which I would like to do. Should spin up a VM. I've got GNS right here. My server is down right now though. A real world boot sector has code for continuing the boot process and a partition table instead of a bunch of zeros and an exclamation point. From this point onwards, the BIOS hands control over to the bootloader. Note, as explained above, the CPU is in real mode. In real mode, calculating the physical address in memory is done as follows. And I don't know how that's different. Yeah, it's the same. Looks like it's the same as what was up here. Oh yeah. So this is talking about real mode. I don't know why that was necessary to point out. Just as explained above, we have only 16-bit general purpose registers, which has a maximum value of 0x FFFF. So 16, 32, 64, 128, 256. So yeah, this would be 255 in decimal. So we take the largest values, the result will be that. Let me just check those 255. Oh, actually, no, it's 16 bits on, so it would be 65535. 255 would be just 2 Fs. Yeah, okay. These are large numbers, just converting them in my head is not a useful skill. So if we take the largest values, the result will be that, where that value is equal to 1 megabyte plus 64 kilobytes minus 16 bytes minus 1. An 8086 processor, which was the first processor with real mode, in contrast, has a 20-bit address line. Since 2 to the 20th equals that number, which equals 1 megabyte, and 2 to the 20th minus 1 is the maximum address that could be used because you don't have a digit for the next place value. This means that the actual available memory is 1 megabyte. In general, real mode's memory map is as follows. So here's the real mode interrupt vector table, the BIOS data area. This is unused. This is our bootloader. This is unused. So like if you're a hacker, if you want to F around with this, here you go. Use, this is space where you can build in a use that was not intended. Then we've got the video RAM, VRAM memory, the monochrome video memory, color video memory, video ROM BIOS, BIOS shadow area, and system BIOS. At the beginning of this post, I wrote that the first instruction executed by the CPU is located at that address, which is much larger than that. How can the CPU access this address in real mode? The answer is in the core boot documentation. At the start of execution, the BIOS is not in RAM but in ROM, which has enough space. It has more space, apparently. Okay, so the next section is the bootloader section. That's it for this video. It was about 45 minutes, which is really long. I'm tired. None of that was relevant to me, but hopefully things get better. And if they don't, hopefully this doesn't take all that long to read through. So thanks for watching, and see you in the next video.